Hello everybody, I wish you a warm welcome to our KiCad tool training about the layout editor in GABA viewer. Let's have a look at our agenda for this training. First I want to speak about the layout task and its working steps. Then about updating your schematic with information might be already changing, only going from entering schematic to layouting. Then I want to speak about the layout constraint and the mechanical aspects. Two things which have to be fixed before you start any layout. Actually perform the routing, hence the layout of our board. We prepare the board for production and generate the GABA files and review our GABA files. Once this is done, you basically have all information you need to do your own PCB, and I will give you an exercise in order you can train your skills on your own. At the very end, last but not least, I want to give you engineering best practice in order you can avoid the most typical pitfalls in layouting a PCB. Now let's start about layout task and its working steps. Layouting means after entering our circuit diagram into eSchema, which we have already done in the last part of this training. You get also the layout constraints. So we give you this constraint. The board size has to be 52 millimeters by 25 millimeters. We use 4 mounting holes in the corners with a size of M3. We use a 2-layer PCB, so this means we have a 2-layer PCB, one top layer and one bottom layer. The top layer you should use for signal routing, and the bottom layer is reserved as a ground plane. So once you have this information, you can start the layouting and have only to enter the manufacturer's constraints. But have a look at this task when we speak about the working steps. Now on the right side of this slide, I summed up all working steps in detail, so let's go through them once. First, you have to update your schematic with any changes, already arriving by going from entering schematic, going to layout. Then you have to clarify the PCB constraints, your own ones and of course the ones of your manufacturers, in order your PCB can be produced. When you start the layout, the first thing you have to do is to care about the mechanical aspects. So you have to decide which board dimensions you have to use, and you design them into your layout. You have to place the mounting holes. Then you import the net list. This means you import the footprints into your layout. Once the footprints are in the layout, you have to place the components. This means you move the footprints on the layout in a way in order to have less crossings as possible from signal wires, because this crossings has to be treated extra. The crossings you cannot resolve by placing the components on the PCB in a good or ideal way. You have to resolve in step number 7. After this, we start the routing of our signals. When you finish the routing of all signals, you fill the free areas with ground or another potential plane, so that the idea is that on the PCB all kappa fields or areas have to have a defined potential. 10. Add the project information on the top of the silk layer. This is really essential because we need the information as the developer's name, project name, date, and your student's number in order to know who's belonging the PCB after the production, who's the owner of this PCB after the production. Otherwise, we have no chance to give you back your PCB. Once this is all done, the PCB is more or less finished. You have to perform the design rule check. This means you check if you have followed all the rules of the manufacturer's constraints by layouting your board. So this check has to be finished with 0 errors before you export to the GABA files. So please take this very serious. If you have any design rule check errors, please make sure you get rid of them before you export your GABA files. Once you are design rule error free, export the GABA files. Before you give them to the manufacturer, again you have to check the GABA files with the GABA viewer. Why this last step, number 13, is so important? Because the manufacturer only checks if he can produce this PCB mechanically or chemically. but he's not going to check anymore if it's electrically performing its intended function. So to ensure that still the function is performed by this board, you have to check this layout before you give it to the manufacturer. Of course, these working steps are found in our agenda. Step 1 to 2 are found in the layout constraints. Step 3 to 4 are covered by the mechanical aspects. Step 5 to 9 are covered in the section about routing. And step 10 to 13 are in the section of prepare for production. Now let's talk about updating your schematic. First of all, what does it mean updating your schematic? Before we go into detail, I have the experience that when you are at the point to enter your schematic into eSchema, you have the electrical functionality or digital functionality, or let's say the system functionality in your mind. What does it mean? Maybe you have simulated the circuit with LT-Spice or another circuit simulator, and now you want to enter this circuit on a PCB or make a PCB for the circuit, and you are sure it's working. So you have only the functionality and the electrical correctness of your circuit in mind. But in the moment you are shifting from simulating entering a circuit into schematic to producing a PCB, you have also to keep in mind mechanical details and also details about how to test this PCB. So that's why I say the checks you have to perform on your own or with a colleague or a team member before you start the layout are at least question yourself, has anything changed? Check number 1. So this means, for example, you decided to change from through-hole technology to SMD technology for some parts. That's something you discuss with your team members. Then secondly, what's about testing? That's what I just said in the introduction to this part. Think about, you want to test this circuit. You power them up and you want to check if it's working. Likely at bigger circuits it's not working at the right moment, so you have to start search for errors. In order to do this, you might be happy you have access to some signals with test points, and it might be possible that you have no access to these signals without adding especially test points to this layout. So what's about testing means just entering test points into your circuit design. The third point is what's about assembling. This means you should take in mind that you choose components and place components in your PCB in a way that they are manufacturable. So for example, if you have a small SMD resistor next to a big electrolytic capacitor, this might be hard to assemble if you first assemble the capacitor and after you want to solder this little SMD component next to the capacitor. So this is in the case of hand soldering. Also, if you have production in a automated production of series production, you have at least to think about one step about if this board is possible to assemble, whether it is soldered by hand or automatically. So this checks you have to do on your own. As I said, question yourself these questions. The best is you question this on your own. You enter the ideas and then you discuss this with your team members or project leader or colleagues to have a better idea about it. In our case, we question ourselves, and I decided that we change the SMD technology for power supply. What does it mean? When you remember, LED number 3, D3 and R4 are checking if the power supply is on or if the circuit is powered, and we decided to use through-hole technology on our board. And my change to you is now we change this through SMD, so we're using LED in SMD technology, and the resistance R4 also is an SMD technology. The idea behind these changes is honestly, I would like you to also learn how to hand solder simple SMD devices as a skill task for you. Secondly, we want to insert test points, and you have to think about which signals should be tested. One signal which might be tested is the output signal, to see how is the how is the voltage versus time with an oscilloscope, for instance, or the intermediate signal, because the circuit is relying on this RC constant, and we are discharging this capacitor to determine our period. So might be it's interesting to see what's the voltage across the capacitor or at discharge and threshold pin. So you see I ended exactly at this point I mentioned, test points. This is the threshold signal, this is the discharge pin, and here we have the output of our circuit. These are the three signals we want to test in our powering up of our circuit. Another point is if you want to test with an oscilloscope probe, for example, you need the signal and you need the reference voltage, and as a reference mostly you take ground. So we also add ground testing pins here. Now you see I added 2 ground testing pins. That's the idea behind, there's this idea behind, because ground testing pins are never enough on one board. For example, you want to test 2 or 3 signals, you had to connect 2 or 3 probes of an oscilloscope to ground, so 1 ground pin might not be enough. So at least add 2 or 3 ground pins on your board. So that's about testing and changing your schematic before you start layouting. And of course, when you go from your schematic, ARC free schematic entering to making updates, this new schematic of course has to be electrical rule check error free, and after this you increase your version number, please. I normally do to increase the version number from 1.0 to 1.1 when I go to the layout of the circuit. Before we start layouting, I just want to review quickly the update of the schematic for the layout. You see here the connectors for test points for the ground signal or for the ground. It's just simple connectors, 1 row, 1 pin added to the ground. To the output signal, to the discharge signal, and our threshold signal. Further, I want to check if the board information is correct. And here we see it's revision 1.0. That's not correct. We have to change, and we have the wrong date. So we edit the worksheet settings. We update to the date of today. We update revision or version to 1.1. Okay, now the revision changed, data changed, that's fine. So we fit to screen again and we save. Now let's go and talk about the layout constraints. In order to enter the layout constraints, you have to start the layout editor, and you can do this in 2 ways. First, you can start it out of the KiCad Project Manager on clicking on this icon for the layout editor, or you are already in the EE schema worksheet and you are clicking on this icon. Once the layout editor is running, you see in the upper left corner this icon with this wheel, and you click on this wheel and the board setup menu is opening. And in this menu you enter all layout constraints, the layout constraints of the manufacturer and your own ones. So let's have a look at the board setup menu. First, we look at the manufacturer constraints. You get them either from the website of the manufacturer, or you make a phone call, email, or you got a PDF, whatever, from your manufacturer, or you request specifications for a board you want to design, etc. We assume a board thickness of 1.6 mm, which is quite common for double layer PCBs. Before we now start to enter all our specified design rules or layout rules, I want to state before, when you open up and run KiCad, the most of the design rules which are already preset are possible. So this means the presettings are in a way that most of the manufacturers can produce a 2 or 4 layer PCB with the default setup of KiCad. So what I want to say is you have to check, in our case or in your case in the very first time, if this design rules are hold or not. Likely they are hold. When you start to make more complicated designs, let's for instance with very thin tracks or something like this, then you have to go to a manufacturer and ask if this is possible to be produced or not. Okay, so I stated again, your project constraints, board size, mounting holes, copper layers. What's interesting here is the copper layers. For us, we use 2. So in the board setup, I highlighted the points we are going to check for our design rules. This is layers, design rules, and solder and mask. Now we are in the layer menu, layer point. We decided to have a 2-layer, parts on front and back, that's possible. We select copper layer 2 and we say board thickness 1.6 millimeters. You can select here FCU, this means front copper, and BCU means bottom copper. CU is because of the element copper in the periodical system of the elements. Copper is CU. Once we have entered this, we click on design rules. Now you see here some checkboxes to be checked or unchecked. We check prohibit overlay courtyards. This means you have to hold the distances around the different components when you move the footprints. So maybe the component is bigger than the footprints. You have a courtyard around this footprint that you place the component in a way that it has enough space to be placed. So you cannot overlap courtyards of components, which makes definitely sense when you start your layout or when you are a beginner. Okay, so yeah, then you see here design rules for the track size, for the diameter of drills, for the diameter of micro drills, and the distance between 2 holes. This is the left side, this is the KiCad menu. On the right side, I picked up some specification from a manufacturer. You see here the hole diameter, smallest drill diameter, distance between lines, thickness of the track, aspect ratio between inner circle and outline circuit for different holes and components. Now let's check. We say we have a minimum track of 0.2 millimeter in our specification. If we go to the right side of the manufacturer's data sheet, we see a minimum track of C, it's figure C. So we have 2 numbers, 0.255 or 0.156. You have to question again yourself, it's why these 2 different numbers are used, because one is in millimeters and one is in mil. So if you see here, then you have minimum, minimal, and standard. Standard is for production with the standard process. Minimal means you can go smaller, but of course it's getting more expensive. So we decided to keep the standard process, and we entered 0.2 millimeters. We see here the minimum allowed is 0.15, so we have already here some headroom for our design to ensure that we get back nicely and good PCBs. This is another point I want to give you as a best practice at this point. Don't lay out only in the minimal possible trace width, because this means it's manufacturable, yes, but if you go to series production, you might have a lot of boards which are not working because these connections are broken. So to have a reliable, stable production process, it's also very important not only to trace all tracks with the minimum width. Minimum width should be used in the moment you have to go through some tiny spaces. Okay, so keep this minimum tracks for very nasty and exceptional situations in layouting. Otherwise, take the minimum track width from your own side a bit bigger than the 4C minimum track width from the manufacturer. this relates also for the holes and drill sizes, etc. Okay, so we have checked this. Then we go to the minimum wire diameter. We have 0.4 millimeter, minimum wire drill is 0.3. So we go here, smallest drill, and we see this is a figure A. We say it's at 0.2 millimeters, 0.3 is standard. We have selected 0.4, so this is fine, and we have 0.3 for the drill, that's fine too. The micro via we are not using, so we don't check this. A minimum hole to hole distance fits, and we don't check this again. Now let's talk about the solder and mask paste distances. On the left side you see the menu. We have a solder mask clearance, solder mask minimum width, solder paste clearance, and solder paste ratio clearance. The bottom 2 points we don't take care about. We leave it like it is preset. We check our solder mask clearance, 0.05 millimeters. Solder mask clearance means the distance, the space between your copper pad, copper soldering mount, and the solder mask. So this is figure D. You have here a piece of copper. This is your solder mask, green, and the distance or the clearance between them is measurement D. If we check again, minimum gap on solder surface D, minimum, we look for standard, we have 0.03, and we entered 0.05 millimeter. So red, we have a little head room here, so that's fine. Solder mask minimum width, if we check here, solder mask minimum width, this should be figure A. Solder mask ridge standard 0.07, and we have 0.25 selected, so this should be fine also. If you are unsure about these figures in your menu and the figures from your manufacturer, which may be named different, this drawing might help you, or clear this with your manufacturer before you start your layout. Now we come to the point entering the track and vias. Based on the constraints, I would recommend to add 2 track width as a presetting for your layout. It's 0.2 millimeters as is the minimum track width we want to use, and 0.5 millimeter the track width which is used for power distribution, or if you have signals which have a more power or a higher current. Add them here, like this you have presets later in your layout. Now let's talk about the mechanical aspects and how to enter them into our layout editor. For the mechanical aspects, you see here what we want to enter in our layout editor. You see the yellow line, the board outline, which is drawn by selecting the H-cut board outline. You select the H-cut on the right side of your layout editor. And you see the 4 mounting holes in the corners of your PCB. And they are spaced 5 millimeters from the outlines. So this means this hole is 5 millimeters from the right, from the left, and 5 millimeters from the top. The same holds for the other 3 holes too. And now I want to show you how you do this with the layout editor. It takes some time, and then the PCB layout editor window is popping up. First, we enter our worksheet information. We change the date. We enter the revision, which is now 1.1. We enter the title, any 555. We enter the company, HDA Prof. Again, I use the tabulator to change between the different fields. And okay. Next, we make fit. You see that the worksheet information is in a very dark red color. We should change this first, so we can go on the right side of our PCB layout editor. We click on worksheet with the left mouse key. You can select or deselect as usual, check or uncheck. you click on the right key of your mouse, you select change render color for worksheet, and here I recommend to use the red number 4 in the defined colors. Click OK, and your worksheet is much more easy to see on your layout. Now we have to enter the board dimension, the outline board dimension. So here it's important that you change the grids from 10 mils to millimeters. In order you can enter the board dimension in millimeters in 1 millimeter steps. And to start, we go to layers. We select H-cut, already elected. So this is the board outline. You start somewhere in the middle. And now you select the polygon. And go start with the left click. You have the polygon. And on the left corner of your windows, you see the length of this line. So at 23, 25, 30, going up to 52 millimeters. You left click. Now you go up 25 millimeters. Left click, going back. Left click and going to the starting point. Finishing with a double click. And if this tool is still selected, you hit the escape key. So now you have entered the board outlines. And now we have to enter our mounting holes. Okay, before we are entering now the mounting holes, I want to show you something I missed up maybe. You see this the normal mouse cursor, you have the cross and the mouse tip. And now it's very handy to have a cursor which shows you X and Y lines. So you click on the left side on change cursor shape. And now you have these lines which shows where cursor position is. So what we do now is we place 4 mounting holes in the corners of your outline of your PCB, and the hole should be 5 millimeter distance from the outlines on both sides. So 5 millimeter from the top and 5 millimeter from the left, and 5 millimeters from the bottom, 5 millimeters from the right, and so on. So to place this component correctly, we are going to select placing components icon. And now the mouse tip changes to our pen. We want to add something, and now we use our position on the sheet. You check at the bottom and you see its X position is 100, Y position is 75. The origin is somewhere on the upper left side, and counting positively to the right and to the right and downwards. So this means we have to enter or to make the center of our mounting hole to the position 105 and 80. This means we go 5 millimeters in the X direction, so we go to 105, and we go 5 millimeters in the Y direction, so we go to 80. 105, 105 and 80, and now you click on the left mouse key, and the library is loading, the component footprint library, and you can scroll down to mounting hole. We select mounting hole, and we take mounting hole M3. Okay, and if you don't move now or just left click a second time, you place the mounting hole where it should be. So now it's very handy to have these lines, because we go directly vertical on this line to the bottom. The bottom position is 100, so we have to go 5 millimeters up, so we go to 95. we click on the left key again, loading the footprint library, and now it's very handy. The last item you have selected is already selected here, recently used. Click OK. And if you don't move again, you have to hold the mouse quiet. You just click the left key and the mounting hole is the right position. Now we move to the right side on our vertical line. The end of the board is at the Y position 95, so we go 5 millimeters back to 90. Oops, sorry, I missed it up. So we had 152 millimeters on the X position, and we go back 5 millimeters, so we go back to 147. Here 147, 95 is the point. We left click. We select our mounting hole, click OK, and the left click OK again. The third hole is placed, and now we go up to the bottom line. That's still the position 75. We add 5 millimeters to 80. We left click and just left click again. Select, sorry. Now I move the mouse, you see. But now we know the position 147, 80 is correct. And we left click and we deselect our tool by pressing the escape key. So that's how we positioned this for mounting holes, 5 millimeters space from the board outlines. Well, we zoom in to the middle, and now we are ready with the board outlines with the mounting holes. So we entered our mechanical aspects. Before we start now to place the components, it's very important to change the grid from 1 millimeter to 10 mils. So we take this one. Why is it important? Because the spacing of our pins, of our through-hole technology mounted devices, and especially for our core unit, our IC with the 8-pin package, is spaced in 2.5 millimeters, in 1 mil. So this means if you select this size, you have 10 grid or 9 grid points between the two pins of your IC, and the pins are directly on the grid. So this means it's a good thing to select 10 mils now before we enter the components. Now we can start the routing of our PCB. Routing, importing the netlist. On the left side of the slide, you see the screenshot of our layout program where the netlist is already imported. If you look at the components, you see the soldering pads. Then in a, let's say, green color, you see the outline of the components. And in a white color, you see the bounding box or courtyard, which indicates the distance you have to keep to place the components later on your PCB. The last thing you can see are these little light white lines connecting different points or different solder pads on the PCB. These lines are called flywires. Why? Because the flywires indicates which points have to be connected electrically during the routing. And now this is the point where we are getting a two-dimensional problem. If you, for example, follow this fly line from pin number 4 VCC up to pin number 8 VCC, we see this flywire is going to cross this flywire 1, this flywire 2, and this flywire 3. So this flywire from 4 to 8 crosses 3 other flywires, and in a two-dimensional problem, this means these flywires or the tracks later hit each other, so we will create a short. Now the task is as simple as it is difficult. You have to place the components in a way that you remove all crossings of the flywires. And that's when puzzling comes into the game. So if you like to puzzle, you really can show your strength in puzzling by removing the crossings of all flywires. Remember the layout constraints. We have a 2-layer board. The top layer is for subrouting and the bottom layer is for the ground plane. So especially as in every game, you need some rules how to play the game of puzzling the components. So the aim of our game is resolve all crossings of the flywires, and the rules are the strategy for our game. Keep in mind that the bottom plane is the ground plane. Why this is important rule for our puzzling? Because if we look, for example, at the capacitor C2, we see that the pin number 2 is directly connected to ground. But it has also 2 flywires connected. Since we know that the bottom plane is going to be the ground plane, these flywires later just disappear when we fill in the ground plane, because they make a direct connection to the ground plane from here to the bottom side of the layout. So we can neglect these 2 flywires, or in general we can neglect all flywires for the ground plane. So this is the first point. The second point is we can resolve crossings by changing the order of the components to resolve the problems, the crossings. So this means just we have to replace the components in a way that we resolve most of the crossings which are not caused by ground flywires. To start the placement, it's a good idea to print out the main part of your circuit. So in our case, it's the NE555 timer with the timing circuit and the output circuit. And also to print out the footprint of your IC and put both in front of you. Why this is important or a good idea? Because if you look at the schematic symbol of your NE555 timer, you see that the pin order 2541673 doesn't correspond to the order of your pin numbers at the package. 1, 2, 3, 4, 5, 6, 7, 8. So a good idea is now to see which pins are laying together, or let's say which pins are close to each other and if there are components connected between them. So if we check our circuit, we see that pin 6 and 7 are closely together, so they are next to each other. And we see that here are R2 and D1 are connected between pin number 6 and 7. The capacitor C3 is connected to ground, and from R1 the pin 7 is connected to VCC. So if we now go to our footprint, we see 6 and 7 are closely together, that's fine. And pin 8 is connected to VCC, and this means we can place R1 between pin 8 and VCC. This means with these 3 pins we can nicely place R1, R2, D1, C3. Only one question is left: what's about pin 5? If we look in our schematic, pin 5 is going to be not connected. So that's perfect. We can place this 4 components on the right side of your integrated circuit. What's left on the left side? We see the ground pin, that's fine, we connect directly to the bottom layer. The trigger pin, pin number 2, is directly connected to the threshold pin, so there's no component between it. At the output, we only have to consider resistor R3 and the LED D2, and the reset pin, pin number 4, is constantly held on VCC by only a track line. So once we have this rough view about our layout, on the right side we have the timing circuit, on the left side we have the output circuit. We start with placing in our layout editor. Since we see that we have more components on the right side of our IC than on the left side of our IC, we don't put the IC just in the center of our PCB, we put it a little bit left of it, so we have enough space for the timing circuit here, and we have a little bit space for the output circuit here. 2 things which we haven't considered yet are the test points. So here the test points, they were placed as good as possible if we have once laid out our main circuit. And the other thing we haven't considered yet are the LED D3 and resistor R4 for the power LED if the power is connected. this routing is also done after we have routed our main circuits, since a connection from VCC to ground is not that difficult to realize, especially if we use SMD technology as in our case. Now I want to show you how to lay out the right part of the PCB, so we take care about R1, R2, C3 and the diode D1. Before we starting with the layout or the placement of R1, R2, C3 and D1, I want to get rid of the annotation about mounting holes right in our board outlines. So we hover over the text, press the M key and move it outside of our board outline, because this is only a notation for us and it's not going to be printed on the silk screen on our board. So now we have a little bit more place here and a better overview about our components. So we start with R1 because pin 8 is up, so we have starting here with R1 as a first component to be placed. Hover over the component, press the M key, move it to the new location and press the left mouse button to relieve and to place. Then we take R2, we hover over R2, we select it, press the M key, move it to the new location and place it. And we move to D1, select with the M key, and interestingly, if you look at the schematic, D1 is in parallel to R2. If we look at our placement now, we see that the threshold pin of R2 is on the right side and the threshold pin of D1 is on the left side. So to make the connection just neatly nice together, we turn the dial that this pin are on the same side, threshold pin THR, like this. And now we have only left our capacitor C3, threshold to ground, and we can, for example, place this component here. Well, first time let's place it here and have a closer look now at our fly wires. So if we see now the fly wires, we can connect 8 to 1 VCC, no problem. Then we connect pin number 2 of R1 to pin number 1 of R2, no problem. We can go from R1 to D1, pin 2, and then to pin number 7 of our IC. That's not a problem too. And then we look at threshold. So we have the threshold pins here going from R2 to our diode D1 and then to our capacitor, no problem. And from the capacitor to ground, since we have a ground plane on the backside, no problem to layout. But we have here the threshold signal crossing here this lines from D1 to 7, pin 7 of our IC. But it's not a problem since we can route the threshold signal between these two pins to our threshold pad of the IC or pin of our IC. So that's no problem for routing. This looks fine for me so far. Now you are questioning what's up with these fly wires going up here. I suspect these are the fly wires for our test pins. Let's move our test pins to check this. Yes, this is our test pin. We just place it maybe here to get a clean fly wire overview, or good fly wire overview. This looks fine for me now. I am a little bit unhappy with the location of C3, since it's now directly next to the through mounting holes. Why? Because if you want to use a screw, the screw head is coming here, and to screw just next to the capacitor might be problematic or difficult. I prefer to move these three more to this area of the board. So we move these three once again here. we turn it in order that the THR, the threshold signal, is on the upper side like this. And now we have also a good idea how we can route the threshold signal. We just routed outside of all components to pin number 6. As stated before, we are done on the right side. Since pin 5 is left free, or it's connected to nothing, it's not connected. Pin 6 is now routed, pin 7 to pin 8. So we have routed the right side of our board. Now it's time, or a good idea, to clean a little bit up the annotations on the components. I want to show you what silk screen. The silk screen is this cyan color. I turn it off and you see this is the silk screen. So this is the text which is later printed on the surface of your PCB, which we can read on the PCB. So this is something we have to care about, that we can read it properly on the PCB. Something only interesting for the fabrication and the assembling is to know the gray portion. So about this writing we can just deselect it, and we don't have to care about it anymore, since we don't see this later on the printed circuit board. It's only for fabrication. So since we are not going to go to fabrication externally, we can neglect this layer. Okay, what we want to have is a clear writing of the silk layer text. We see here R1, R2, that's fine for me. D1 is also fine for me. We can move the K of the cathode of our diode a little bit more to the right, so this might be nice. Then we have this test point, which is J1 very near to the R2. We can move the test point actually a little bit. Out of this area, and this can be between the screw heads, which makes no problem. We place it here, and maybe we move the text on the right side of the test point to make it more distinguishable from the others. What we can totally remove on my side is the reference for the mounting holes. This is not necessary in ours, so we select and we say cut. No. This is a little bit difficult since the text is directly linked to the symbol of the mounting hole. But if you hover over it and select E, you can select the layer, and we just move it to the drawing layer user, which is empty, or we don't use it at the moment. So E, selecting layer, drawing user, okay, and we deselect on the right our user layer, so we also getting rid of these annotations. After the placement of all your components, your layout should somehow look like this. All footprints are inside of the board outline, and the fly wires crossing are reduced to a minimum. They are removed totally at its best. From our initial placement, I have to change a little bit to place the other components. First, I placed U1, our integrated circuit, a little bit more to the downside of our PCB, because I wanted to place C2 and J1 close to our integrated circuit. Why was this my wish? Because C2 is a stabilizing capacitor to filter out the ripple on the supply which is coming in from our supply connector J1. So in this case it's very important to close this stabilizing capacitor on the one side close to the integrated circuit supply, so this ground pin and the VCC pin on the one side, and on the other side close to your power supply connector J1. So this would be the perfect alignment of these two components, and that's why I moved U1 a little bit downwards. Further, I had to move a little bit our charging discharging capacitor C3 in order to insert a test point for the ground here, and I moved our J2 to test the threshold signal THR a little bit between the two mounting holes. On the output side of our circuit, I layouted R3 and the diode 2 on the left side, and I also inserted some test points for ground on the left side and J3 for the discharge circuit, discharge signal on the left side. The LED indicating that power is connected and the resistance for the LED are layouted as surface mounted devices as explained, and they are layouted in the upper left corner of the board. After having finished these placements, you should ask yourself some questions. First, is assembling possible? This is for hand soldering not so much important, but later for production of series products it's very important. But for us, what's important for us is it possible to access all test points? If you think about accessing test points, it's the most easiest way is to place the test points close to the border of your board. Like here for J4, you can easily access it from the top. Like J2, you can easily access it from the right. Like J6, you can easily access it from the bottom. Like J5, you can easily access it from the left. J3 is a little bit extra ordinary because it's not so placed. It was not possible to close it closely to the border of the board since we have here R4 and D3. But since R4 and D3 are surface mounted devices, they are not so high, so I think it's as easily accessible J3 from the top like this. The next thing you have to check before you further proceed your layout, make sure all texts are readable in landscape, which is the case in this layout. All silk layer texts in this cyan color are readable in the landscape, or if you turn your board 90 degrees in this direction, in clockwise direction, to portrait to read them. So the next step is to pour the ground plane. This will lead to the point that all the fly wires for the ground signals are gone, and then we have to check if there is still some crossings of signal fly wires, which we then have to resolve with other techniques. So now we are ready to pour the ground net on the bottom layer. In order to do this, we have first to change our grid back to millimeters, because with this grid in 10 mil size, we don't get this corner because it's in the 1 millimeter grid, so now it's off grid. So we change back to 1 millimeter. Then we have to select the bottom cover and we select the add fill zones. We start in the left corner with a left click on the mouse. Then we have to select the properties. We say we take the ground net for the filling. All other settings we leave unchanged in the default value, that's fine. And then we fill the ground plane by just following on the H-cut layer or the border, the outside dimensions of our board. Once you are finished, we deselect our filling tool with escape. Now we see the fly lines in white. What's interesting for us is now how it's looking on the top layer. If you look here, we can check the top front layer or top layer. And now we have to check the fly lines for any further crossings. It's easy to start with the power supply. We have here the power supply jack. Here we see the fly lines for the surface mounted devices. That's no problem, that's easy. We see the fly line VCC going to pin 8, that's fine too. If we look at the outside, pin number 3, output of our IC, pin number 3, we see R3 and the diode, that's fine. The test point to the pin number 2 of the resistor, that's fine. if we look at our timing circuit on the right side of our PCB, the VCC is going to R1, and that's fine. R2, test point for pin number 2 of R1, pin number 1 of R2, that's fine. Then threshold, pin number 2, parallel the diode, we have the connections here, the connections here. Then we go to pin number 7, the discharge, that's fine, we have no crossing. And we go from threshold test pin to the threshold point of the diode to the capacitor to our threshold point, so no crossing. If we look now, the threshold signal goes to pin number 2 from pin number 6, and the VCC, the supply pin, goes from 4 to 6, so here we have a crossing. We have to think about this crossing, how we can resolve it. If you check the data sheet, you will see that the supply pins are pin 1 and 8, and pin number 4 is the reset pin, which is held to VCC to not to make a reset of the IC during operation, and that's fine and very good, because this means this pin doesn't consume any power. There's more or less a static connection. So I would suggest in this case we route a threshold on the front layer or top layer just under the IC from 2 to 6, and we lay out the VCC pin to the VCC pin number 4 on the bottom layer, and like this is a very clean layout. After pouring the ground plane on the bottom layer, we are getting back this layout with the fly lines. Here all crossings are resolved as shown, until the crossing here from the threshold signal from pin 2 to pin 6 and the VCC signal from pin 4 to pin 8 of our integrated circuit. As said, we are going to resolve this by routing threshold on the top layer or the front layer, and by connecting pin 8 and pin 4 on the bottom layer, since pin 4 is only the reset pin, which is a static signal kept high by VCC. Further strategies to resolve crossings might be routing between pins, routing under components. This means, for example, you can also route here to make a routing under this component on the bottom layer and on the top layer. And third, if possible, you can route the power supply also on the bottom layer, what we did for the connection of pin 8 and pin 4. So the next steps are signal routing on the front layer to get rid of all fly wires, and then pouring also ground plane on the front side to fill up all the free areas and connect them also to ground. Starting with the routing of our left fly wires, I decided to start with the power nets, and then I will route the signal nets. In order to do this, first remember to change back your grid from the 1 mm grid back to the 10 mm grids. And for the power supply, we choose the wide track with 0.5 mm, that's fine. Then we select the front layer or the top layer, and we select the route track tool. We start with routing our VCC. You just click with the left mouse click and you can route and to the VCC pin. Now we said that we want to route from pin 8 to pin 4 on the bottom layer, so we change the layer. The blue arrow, the blue triangle here indicates the selection for the tool where you want to work in which layer. So we route from pin 8 to pin 4, and now we see something funny. We have a ground connection, and through the ground connection there is this routing, but we have no spacing, so we created a shortcut. To resolve this, we deselect our tracking tool by pressing escape. we select the port area with the left mouse click, and we click on the right mouse key, and we select zones, and we select fill, and then we got the spacing in order not to create a shortcut. Well, so that's how we routed our VCC signal, and the ground signal is connected by the complete back plane or bottom plane. So now we go back to the front side. We select again our track tool, but now we change the track width from 0.5 to 0.2 millimeters, and we are going to wire all other fly nets. Start here, power connection, test point R3, and so on. Threshold pin. So like this, all signals are wired or routed. I didn't route this pin ground because we are going to fill the front layer, fill the free areas on the front side also with the ground plane, and then this will be automatically collected to the ground plane. In order to do this, we have still selected our copper front layer. Then we select our filling tool. This time again we have to change to the grid of 1 millimeters to get the corners. We start again on the left upper corner, click on the left side, and we select again the ground net. Okay. And then again we follow our H-cut layer for the ground filling on the front side. Once this is done, we deselect our filling tool with escape. And now you see that all the ground pad of our resistor or diode, I don't know what it is, but it's also connected with this 4 pieces or legs. This is maybe interesting to see because you can also say, okay, well, the whole ground plane is the whole front plane is ground. Why do I have these spacings? Well, that's a topic of soldering, because if you completely connect this pad to ground, if you want to heat up this pad or this area, let's say you want to heat up this area for soldering, and you don't have the spacing, you need a lot of power because you have to heat up the complete area, because copper is a very good heat conductor. So that's why you make the spacing, so you only heat up, or the heat can only go from this pad outside over the small fingers, which is hard to heat up the rest of the copper, so you can heat up only the pad to solder your SMD. Well, but that's all we have to do. We can turn on the copper layer. Now is done. You want to see the silk layer for how it's looking when its board is manufactured, so you click on the silk layer, and now your board is more or less ready for production. Once you route all signals on the top layer and on the bottom layer, you filled the bottom layer and the top layer with the ground plane, your circuit is somehow looking like this. The routing is therefore finished. What we have now to do is to prepare our board for production. So the next point is prepare our PCB for production. Prepare for production. Everything is correct. So this includes mainly 2 steps. First, we have to add the project information on the silk layer. This is a project name, author name, date and version. And we have to perform the DRC check to see if we have followed all design rules from the manufacturer. So to prepare our board for production, we have to do two things. We add our project information and we run the design rule check. In order to fill in the project information, we select the silk layer and we select the text tool. We say we want to place the text here. We fill in our project name, any 555, author name, designer name, how we want to call it, developer name. It's revision 1.1, and we put the date of the date 09/04/20. Hit OK. We have to turn it, rotate, and we see it's too big. Doesn't matter. We deselect our text tool, we hover over it, and we press the E key to get into the properties again. And we say text height and text width only 70%. And if we hover now over it and move it with the M key, it fits on our board. So this looks not bad. We deselect the tool by hitting the escape key. Now we perform the DRC test or check, design rule check. We click on the bug, DCR control menu pops up. The minimum track width, minimum VR size, minimum micro VR size are taken from the board setup. So we keep this. We check all this checkboxes because we want to be sure. And we create a report file because I would like to see this report file before you enter the PCB for production. So we run the DRC, we save the report file, and we see finished without any errors or problems. So we say close, and now we can generate our Gerber files. Before we generate our Gerber file, it's also a good idea to use 3D viewer in order to see if we can place the components and how are the test points accessible. So you click on View, 3D viewer, and then we get a first look at our layouted board, which looks pretty. We have here our socket, our C2 capacitor, our two surface mounted devices, our pin headers, capacitor, and the pins. We can turn them a bit, and you see, thinking about access, if you think about, you have here the screw heads, you still have possibility to access this pins for testing. Also, if you go on this side, if you think about it, you have a screw here, you can access from this side, and the small SMD parts you can access from this side or even over the screw. Here you have the pin headers for connecting the power supply and our stabilizing capacitor. So this looks fine. We see the traces, the distance, and the silk layer, and you also see that this is the pad, which we can see the copper, which is plated in gold in this case, and here you see the opening for the soldering, and here it's covered from the solder mask. So you see, if you might be hard to have connection to this signal or to this signal without this test points, and also it might be hard to have ground connection without this test points. Okay, let's look at the bottom side. This looks also nice, and we see here our connection from pin 4 to pin 8. Once your board is ready to generate the GABA files, I cannot stretch enough the point to insert your project information in order you can get the board back from the manufacturer and we know to who belongs this board. Further, to generate the GABA files, you select in the file menus of the PCB new layout editor plot, and the plotting menu is popping up. Most of the settings we just leave like they are. We select the plot format GABA. We output into a directory in which name the revision number is written. We select use extended x2 GABA format. We select show all messages. And finally, we first plot the GABA files, and then second, we generate the drill files, because these are the files for the drilling the holes in the PCB. Now we generate the GABA files. Click on File, on Plot. The plotting menu is popping up. We select the GABA format. We select our output directory. We check use extended GABA format. We select show all messages. Then we plot the GABA files. Then we generate the drill files. Also in this menu, we leave the setting as they are. We click on generate drill files. We close. And we have generated the drill files and the GABA files for our PCB. In order to view your GABA files, you go to KiCad Project Manager and you select the GABA viewer. Now we want to check our boards and if the generated GABA files are correct. For this, we click on the GABA viewer icon. The GABA viewer is popping up. And now we have to open the GABA files. So we go to File menu, open GABA files. We go to our GABA files directory. We want to select all files, so we hit Ctrl A. And our board is shown. And now we have to deselect some layers in order to get a better overview. For this, we go to the right side of the window. We click the right key of our mouse and we hide all layers. And then we start with the H-cut layer. So we have our H-cut layer. We zoom a bit out in order to see the whole board, or we go to page width, it's better. Then let's start with the bottom copper. We select the bottom copper. So green, we see now the bottom copper. This is the copper field, and you see where the spacing, this is etched or trimmed with laser or cut, however, out of the copper, and what remains is the green area. So that's fine. Now interesting is the solder mask, or let's say whether the solder stop mask. And you see at this blue circles or squares, there's a window in the solder mask or solder stop mask. So this means here everywhere you have solder stop mask, and only this blue rectangle or these blue circles are left free. So this means, for example, for our IC, that in this area there's a solder stop mask window and you can solder the pins. Look, yeah, so that's correct. And with selecting, deselecting, you can check if at all holes and all mounting holes or soldering pads you have solder stop mask windows. Okay, the next interesting thing to check is if we have solder passed on the ground side of our board, and we see we don't have solder passed on the ground or on the bottom side. This makes sense since we have no surface mounted devices there. Okay, now we check the silk layer on the bottom side. Also, we didn't make annotations on the bottom side, so we expect we have no silk layer there. That's fine. And when we finished now we are finished with the bottom side, so we go to the front side or top side. First we check again the copper. We select the copper fields, we see our routing, this looks fine. Then we check our solder stop mask for the top side, it's the same game. We check if the windows of the server mask are at the places of the holes and the pads for our SMD. So let's take a little bit care about this because it's new for us, SMD devices. Looks also fine. And at this time we can also check where solder mask is dispensed. Solder paste is dispensed. We deselect the ground paste and we see now that this solder paste is dispensed only over the SMD pads, which is correct also. The last thing we want to check now is if the silk layer on the top layer is also correct. So we select the silk layer and we see that on the top side we entered our name, project and date. So this looks also good. Now when we have check the Gerber files, the next interesting thing is to check if the drills are at the correct place. So the holes which are to be drilled, that's now we go to File menu and we open Excel drill files. It's again in our Gerber files directory. Again we want to select all files, so we hit Ctrl A. Now you see on the right side 2 new layers are inserted, placing NPT drill, PT drill, and we start with this drill, and you see the first drills are the drills for our mounting holes, that's fine, and the seconds are the drills for our components, and we want to check if they have the right place, so we compared for example with the front or top cover, and now you can check it at every pad or at every through hole which you need, you have a drill file or a drill. And now, since we have checked the Gerber files and we have checked the drill files, and we assume or have seen that our board is correct, you can zip the folder with the drill files and with the Gerber files and send it to your manufacturer. Now it's time to start with the exercise. As an exercise, we use the circuit we have already entered into our EE schema in the first part of this training. And these PCB constraints are as follows. The board size has to be 52 mm by 25 mm. We are using 4 mounting holes with a size of M3. We designed a 2-layer PCB. This means the top layer is reserved for signal routing and the bottom layer is a ground plane or reserved for some power supply VCC routing. Please update your schematic since we decided that R1 and LED1 should be surface mounted devices. So select these footprints in the footprint annotator in the schematic. Insert test points to your circuit on the signals which you want to monitor during powering up. And please ensure that you set a new version on the worksheets of the schematic and the PCB layout. Now I want to talk about engineering best practice in order you avoid some typical pitfalls. Ask yourself and your team questions: how to test, how to mount, how to assemble. And the answers to this question should result in an update of your schematic. Before you start your layout, I highly recommend to print out the main circuit, print out the main component's footprint, and make a rough planning where you place the different sub-circuits on your PCB. If you remember, we did this during our training with the ICCs, with the NE555 timer. We put this timer in the center of our PCB and we place the timing circuits on the right of our IC. We put the output circuits on the left on our IC and we put the power supply indicating circuits on the top of our IC. The first time you start your PCB layout editor, you enter the HCAD, you place the mounting holes and you place the connectors. Why placing the connectors is important? If you, for example, lay out an Arduino cape, the connector's position is fixed and the signals on the connectors are also fixed. So this means where is the power supply coming from, where are the digital and analog output input pins, heavily determines the layout process and how your layout is later looking. Put the project information on your silk screen, project name, version, author, date. It's important in order first to get back the correct board, and second, in order to know which schematic belongs to which board. Run the design rule check. Your board has to be design rule error free. Export the Gerber and drill files into an extra folder on your PC. Always check with the Gerber viewer if the exported Gerber files and drill files are correct. Now I want to show you what's also possible. Here you see the A64 Linux Xenu board. It's a 6-layer single computer board with its peripherals and some connectors here. And it's a 6-layer design, and you can find this design and other designs as examples on the KiCad webpage. This is a very interesting resource for you. For example, if you want to look how professional layouters, designers or developers design their boards and how do they connect, for example, a DDR3 RAM memory, or how do they make the routing to the Wi-Fi on Bluetooth low energy module. So this is sometimes interesting to download here the schematics and also the layouts to check how more difficult layouts are done. At the end, I want to say thank you for watching this video and have fun with your PCB design. See you and take care.